Welcome to the 8th part of the series of lectures related to the RM software for filter design. Now we will talk about linear phase low-pass filters with corrected amplitude. After the introduction, we will explain the process of correction of the amplitude of linear phase filters, and we will give 3 examples. Having the transfer function of a non-selective, say linear phase, polynomial filter, one may produce a, in quotes, selective one by adding transmission zeros on the omega axis. In order not to disturb the original phase characteristic, the amplitude correction is performed so that the numerator of the transfer function is extended by adding transmission zeros at the imaginary axis of the complex frequency plane. In that way, the newly synthesized function will have the original poles and new zeros as compared with the prototype. Due to the relatively minor influence of the added zeros to the passband attenuation characteristic, however, a renormalization is to be implemented so that in the final solution both poles and zeros are new. One has to have in mind that usually the polynomial transfer function that approximate constant group delay, being of maximally flat or Chebyshev type, cover a bandwidth much larger than the 3 dB bandwidth of the filter. In other words, in the prototype function, selectivity is lost in favor to constant group delay far outside the passband. As a consequence, the improvements obtained by the amplitude correction have limited scope in the sense that the resulting filter is still not a selective one. Nevertheless, a reduction of the transition region between the passband and the stopband is achieved, which allows for the neighboring transmission channel to be nearer than previously. Since the frequency is kind of natural resource, one may say that in this way a frequency band is saved, or that rising the selectivity has an ecological effect. So let's go to the details. The transfer function of an extended polynomial filter may be stated as T of S, a ratio of two polynomials, Q of S and P of S, and P of 0 and Q of 0 are normalizing these two polynomials in the origin. P of S is the known denominator of order R of an extended polynomial filter, usually approximating constant group delay. Q of S, being of order K, is also known, but may contain only complex zeros, including zeros at the real axis of the complex frequency plane. That means that during the group delay approximation process, we used a specific function which has complex transmission zeros. The RM software allows for Q of S to be unity, in fact allows for the case where there are no complex transmission zeros at the beginning. To keep the phase characteristic unchanged while improving selectivity, new transfer function is to be created in the following way. Now, the original function is multiplied by a polynomial of S, which has zeros only at the omega axis. M is the number of transmission zeros, which are unknown. This will be found through an iterative process for a given value of the minimum attenuation in the stop band. Note, the new polynomial of S does not affect the phase characteristic of the filter. Let's go to the examples now. Here is the group delay characteristic of a 14th order polynomial filter, which is approximating the constant group delay with 2.5% of group delay error. The amplitude corrective polynomial in the numerator of the transfer function will be of order 12, which means 6 zeros at the omega axis will be introduced. As a result, we have here the resulting amplitude characteristic of the corrected filter in the passband. You see from 0 to 3 dB is shown only, and the gain, attenuation and the gain may be seen all over the frequency axis. And here is the overall attenuation characteristic, which is obtained after the iterative process. The second example is related to a maximally flat approximation of group delay. This is a Bessel polynomial. The order of the polynomial filter is 10, and 4 transmission zeros will be introduced for at the omega axis, which means the order of the numerator will be 8. Here is the amplitude characteristic and the attenuation in the passband, and here is the overall amplitude characteristic of the amplitude corrected filter. In the third example, we will look for the benefits of the amplitude correction which was introduced here. The example is Bessel filter of 8th order with 3 transmission zeros, and the minimum stop band attenuation is 40. Here the overall amplitude characteristics are shown for both corrected and original polynomial Bessel filters. To better appreciate the gain, this diagram is now enlarged, and we can see that the blue line is the corrected filter, the red line is this original Bessel filter amplitude attenuation characteristic, and we can see that there is a contraction of the transition region by 22.55%, 22.55%, which is a nice gain, and that is convincing for application of this new amplitude correction procedure. To get a more complete picture, here we see what happens in the time domain when looking to the step response. We see that the correcting function is faster, that the not faster, but the delay is lower, but the rise time is almost the same, and that the Dirac pulse response is quite a little bit distorted. So that would be the end of part 8 of the series of lectures. Thank you for your attention.